Hello everyone, welcome back to my video tutorial. This time I will be talking about ellipse generating algorithm. But before we start with the algorithm, let us try to understand what is an ellipse. An ellipse is defined as the set of points such that the sum of the distances from two fixed positions foci is same for all points. This is an ellipse and we have a foci f1 and f2, and we have a point P x, y, and the distance of P from F1 and the distance of P from F2 D1 plus D2 summated together will be the same for all points. So let us assume another point, and if we are on the ellipse here and a distance is calculated from F1, let us say this is D3 and here D4. So D1 plus D2 will be equals to D3 plus D4. Now let us continue. If we labeled distance from two foci to any point on ellipse boundary as D1 and D2, then the general equation of an ellipse can be written as D1 plus D2 equals to constant, expressing distance in terms of focal coordinates. F1 equals to x1, y1, and f2 equals to x2, y2. We have this as a constant using distance formula. Okay, so here if we use f1 equals to x1 and y1, we have this is f1 and have coordinates of x1, y1, and f2 have a coordinates of x2, y2, and then there is a point here P x, y. Then how do we find the distances? We find the distance between the x-axis first, x minus x1, and on the y-axis also y minus y1. We taking a square root of it, and we summate it, and then we're taking a square root of it. Okay, so this is how distance is calculated. This is nothing but distance formula. All right. Properties of ellipse specifying equations. An interactive method for specifying an ellipse in an arbitrary orientation is to input two foci and a point on the ellipse boundary. With these three coordinates, we can evaluate constant in equation with this formula. We can say ellipse is in standard position if their major and minor axes are parallel to x-axis and y-axis. So we have x-axis and y-axis here, and this ellipse is in parallel to x-axis and y-axis. Okay, here is your x-axis for the ellipse, and then this is your y on the ellipse, and this is your x on the ellipse. Okay, and we know that they are parallel to the x-axis and y-axis. And then ellipse equations are greatly simplified if we align major and minor axes with coordinates axis, that is x-axis and y-axis. So this is your minor axis, and this is your major axis. If we can align them here with the x-axis and the y-axis, and then ellipse equation are greatly simplified. Okay, so we can align it like this. All right. Now, equation of ellipse can be written in terms of the ellipse center coordinates xc, yc, and parameters rx and ry. This is your ellipse center xc, yc, and a parameter, that is radius on the y-axis on the minor axis, and rx, radius on the x-axis or the major axis. Okay, so this is your formula: x minus xc divided by rx whole square plus y minus yc divided by ry whole square is equals to 1. Using the polar coordinates r and theta, we can also describe the ellipse in standard position with the parametric equations. x equals to xc plus rx cos theta, y equals to yc plus rx sin theta. This is another formula for generating ellipse. Property of ellipse symmetry. Symmetry property further reduce computations. An ellipse in standard position is symmetric between quadrant. So we have this is an ellipse, and here we have in the center we have xc yc, and then we have ry on the y-axis. In this particular case, ry is on the major axis and rx is on the minor axis. A radius of the center between the center and the boundary on the x and y axis. On this quadrant we have 0.24. This is the 0.24, 2 on the x-axis and 4 on the y-axis, and this is given as xy. On the second quadrant we know that y will be minus. Here we know that y will be minus, and in this quadrant we have x is also minus 2, and this is minus 4, and in this quadrant we have x minus negative x and positive y. All right, given parameters rx, ry and xc minus yc, we determine points xy for an ellipse in standard position centered on the origin. Then we shift the points so the ellipse is centered at xc, yc. If we want to display the ellipse in non-standard position, then we can rotate the ellipse about its center to align with required direction. For the present, we consider only the standard position. We draw ellipse in first quadrant and then use symmetry property for other three quadrants. In this method, we divide first quadrant into two parts according to the slope of an ellipse. Boundary divides region at slope equals to minus 1. So when we find the slope for this quadrant, first quadrant, when we have a slope which is equals to minus 1, that is the boundary. Yes, now that is the boundary here. We are dividing it into two regions. We take unit step in x direction if magnitude of ellipse slope is less than 1. So we take unit step in x direction, this direction, if slope is less than 1. This is called the region 1. In region 1, slope is less than 1, so here we will take a direction in the x. We will take unit step in the x direction. We take unit step in y direction if magnitude of ellipse slope is greater than 1. So here you will take, in this region, you take unit step in x direction. Here in region 2, we will take direction in y direction. Ways of processing midpoint ellipse algorithm. We can start from 0 ry and step clockwise along the elliptical path in the first quadrant. Clockwise, we start elliptic wise. This is clockwise. Alternatively, we could start at rx equal to Alternatively, we could start at rx, 0 and select points in an counterclockwise order. Also, we can start from x direction and then we can start from counterclockwise order. There is no problem. With parallel processors, we could calculate pixel positions in the two regions simultaneously. So if we start from the y, and then if we also start from the x together, if we have parallel processor, we can calculate pixel position simultaneously. Here we consider sequential implementation of midpoint algorithm. We take the start position at 0 ry and steps along the elliptical path in clockwise order through the first quadrant. So we define ellipse function for center of ellipse at 0, 0 as follows. This is the function for ellipse where we have a center at 0, 0, ry square x square plus rx square y square minus ry square rx square, which has the following properties. If ellipse xy is the function ellipse xy is less than 0, if x comma y is inside the ellipse boundary, and the function will be equals to 0 if x comma y, a point on the boundary, is on the ellipse boundary. Okay, so what we want is this. If the function of ellipse is greater than 0, it means the point is lying outside the boundary. Okay, if it is less than 0, it is inside the boundary. If it is equals to 1, it is on the boundary. And if it is greater than 0, the point is lying outside the boundary. Thus the ellipse function serves as the decision parameter in the midpoint ellipse algorithm. So this function will be your decision parameter. Okay. At its sampling position, we select the next pixel from the true candidate pixel. So starting at 0ry, we will start at 0ry. This is we'll start from here. We take unit step in x direction until we reach the boundary between region 1 and region 2. So if we start from here, we will go this way, x direction, until we stop here, okay, in this particular boundary. Then we switch to unit step in y direction in remaining portion on the ellipse in first quadrant. After that, from here, we will take direction in the y. It will take unit step in y direction. All right. At this step, we need to test the value of the slope of the curve for deciding the endpoint of the region. So whether the slope is -1 or not, that we have to test all the time in the unit step. This one boundary between region 1 and region 2. The ellipse slope is calculated using following equations. This is the slope calculation formula. At boundary between region 1 and 2, slope is equals to -1, and equation becomes like this. So 2ry square x equals to 2rx square y. Okay. Therefore, we move out of region 1 whenever following equation is false. So when this is false, this equation is false, we will move out of that region. All right. So this is your formula. Midpoint between candidate pixel in region 1. Figure shows the midpoint between the two candidate pixel at sampling position xk plus 1 in the first region. Assume we are at xk, yk position, and we determine the next position along the ellipse path by evaluating the decision parameter at midpoint between two candidate pixels. So how do we find this? Is that here we are already here. Now we want to move unit step. We will take unit step because we start from yk, and then we will take unit step here. The next step of pixel position on the x-axis will be xk plus 1. That is clear. So now we have two candidate. This is your first candidate. This is your second candidate pixel. So what to choose among this is that we will take the midpoint here. All right. So we will find whether the midpoint lies on the boundary of the ellipse or not. Okay. So that is the decision parameter. So we have a decision parameter p1k equals to f ellipse xk plus 1 yk minus half. All right. We know that xk plus 1 is an unit step on the x-axis. This is your xk plus 1. And here is your yk. Why we put half is that we cannot decide whether we will choose this one or this one. All right. That is why we cannot decide whether we will choose the top pixel or the bottom pixel. That is why we put half here. All right. So we will take the formula and then function formula, the function of ellipse. We will calculate all these formulas like this, and we will come to the conclusion that if p1k is less than 0, the midpoint is inside the ellipse and the pixel on scan line yk is closer to ellipse boundary. Otherwise, the midpoint is outside or on the ellipse boundary, and we select the pixel yk minus 1. So if p1k is less than 0, we will choose yk, the same line, and otherwise we will go to the bottom one. So let me just if p1k is less than 0, we know that we will choose this one, this point. Okay, we will choose C1. Otherwise, we will choose C2, the bottom one. Okay, that is how pixel moves. All right. Now we know that the ellipse line is this. So we know that the the top one is closer here in this case. All right. So here we will choose the top one. Now, an algorithm for midpoint ellipse generation. This is what you have to remember. Input r, x, r, y in ellipse center, xc, yc, and obtain the first point on an ellipse center on the origin as x0, y0, 0, ry. Calculate the initial value of the decision parameter in region 1 as p10. This is the formula that we already gave. At its xk position in region 1, starting at k equals to 0, perform the following test. If pk is less than 0, then the next point along the ellipse is here. Yk will remain the same. X will take an unit step no matter what, but yk will remain the same in region 1. Okay. Otherwise, if p1k, the decision parameter, is greater than or equals to 0, the next point we will take is yk minus 1. That means if we are here, suppose we are here in this pixel, the next step we are going to take is here. Okay, horizontal. Otherwise, if p1k is greater than or equals to 0, suppose we are already here, the next step we are going to take is here. Okay, k will increase no matter what, but in this case y will decrease. So this is your pixel. Alright, that is how you are going to move. And we will continue until 2ry square x is less than or equals to 2rx square y, because we know that we have in region 1, this is ellipse, we have two bound region. We will move till here. Okay, so region 1 and region 2 will have different formulas. Calculate the initial value of the decision parameter in region 2 using the last point x0, y0. Calculate in the region as like this. This is for region 2. At its yk position in region 2, starting at k equals to 0, perform the following test. If p2k is greater than 0, the next point along the ellipse is xk, yk minus 1. Now here we do not make changes on the x-axis. Alright. However, we will take unit step on the y-axis. Y-axis will decrease. Alright. So suppose we are already here. this pixel and we want to move the pixel. All right, xk will remain the same. So if p2k is greater than 0, the next point we're going to take is here. X will remain the same, yk will changes. All right, yk will decrease, will come down, xk will remain the same. Otherwise, we will take xk plus 1. So otherwise, we are already here. The next step we are going to take is if p2k is greater than or equals to 0, the next step we are going to take is here. Y will decrease no matter what, but either x will increase or decrease either we will increase on the x-axis will depends on the decision parameter p2k. Okay, so using the same incremental calculations for x and y as in reason 1, determine symmetry points in the other 3 quadrants. So likewise, this is only for the first quadrant. This is here. We are only giving algorithm for the first quadrant. So symmetrically, we are going to do it all for the other quadrants. Here we already remember that x will take xy. Here in this case we'll take x minus y. I hope you all remember that. And then here we will take minus x y. In this quadrant we will take minus x minus y. Alright. So move each calculated pixel position onto the elliptical path centered on xc, yc and plot the coordinate values. X equals to x plus xc, y equals to y plus yc. Right. So we will have to repeat the steps for reason 2 until yk is greater than or equals to 0. Now we are given an example. Calculate intermediate pixel position for first quadrant for ellipse with rx equals to 8, ry equal to 6, and ellipse center is at the origin. So origin is 0, 0, no problem. We have the radius ry equals to 6 and rx on the x-axis is 8. Initial point will be 0 ry, that is 0, 6. We will start from the top on the y-axis and we will calculate that p10. The formula is already given, and using this given formula we can find out that p10 is equals to minus 332, which is less than 0. So in this case, let us see, in the first iteration, in the 0th iteration, the decision parameter is minus 332. So we know that it is less than 0. So if p1k is less than 0, so we select yk. The next step for the y-axis will remain the same. Yk plus 1 equals to yk. Else we will select yk plus 1 equals to yk minus 1. Okay, so now it is less than 0. The first value we have is 1, 6. All right, we already know that the beginning we know that y is 6, that is your yk. Okay, your y value, the first yk, which is 6, and it will remain the same. Now we will see whether we have reached the end of reason 1, but it is only the first iteration, so it is unlikely that we have reached this position. All right, and then we calculate again for the next iteration. In this case we are given p1k here. This is the previous one, minus 332, and the rest remains the same. All right, using this formula you simply have to substitute this formula. Remember this formula and substitute it. Now we know that the second decision parameter is minus 224. That means still yk will remain the same, x will take an unit step, but y will remain the same. Okay, like this. So likewise, you will continue to calculate, and then you find that the next iteration is minus 4, 4. That means it is still the same, 6. All right. Next iteration, you will substitute the value of minus 1, 4, 4 here. And then we finally have a positive number, that is 208. That means when we finally have a positive number, we will use this point. That means y will decrease. It will decrease from 6 to 5. Okay. So we will continue to do this, and then we have a negative number again. All right. So when we have a negative number, it remains the value of y remains the same again. Just remember that on this side, x side, it is a unit step. Okay, it changes no matter what, but on the y side, it changes according to the decision parameter. Now we are getting another value, a positive value on the fifth. So we should remember that for each and every iteration, we have to check whether the new value of this is correct or not. All right. And then we have another value, and then y side will decrease again, 7,3. So after we calculate all these things, and then for each iteration, I know that we calculate this value. So when we calculate this value will be true, and then we will move to the next reason true. So p2 0, 2 indicates the reason true. We will calculate the value here, and then we find out that it is negative. So when it is negative, we select xk plus 1 equals to x. In this case, now we make changes on the x-axis, not on the y-axis. Y-axis will decreases no matter what, but we will make changes on the x-axis. All right. So when it is less than 0, we will select xk plus 1 will be equal to xk plus 1. That means the value of x will increase. All right. So it is increasing from 7 to 8, and y is decreasing from 3 to 2. So calculation stops when yk is less than or equals to 0. It has to stop when it reaches the axis. So we calculate again, and then we get the value 361. Now it is positive. So when it is positive, xk will remain the same, 8 to 8. But in this case, the value of y will changes no matter what. That is 2, from 2 to 1. Now we get another positive value. All right. Here, after this, the calculation will stop because yk value will be less than or equals to 1. Sorry, less than or equals to 0, because it will have to decrease from 1 to 0. All right. In this case, it is positive. When it is positive, what do we do is that we will take the value, the same value. Okay, here is same value. That means there will be no change from 8. It will remains 8. Okay, now the calculation has stopped. We have completed the first quadrant. Let us plot the pixel. So here we have pixel here. Suppose this is your 0, 0 here. How do you plot the pixel? Like this is from 0, 0. The initial point is 0, 6. Here is your 0, 6. Right. And next will be 1, 6, 2, 6, 3, 6, 4, 5, 5, 5, 6, 4, 7, 3, 8, 2, 8, 1, 8, 0. Now that is how ellipse is generated. We have seen how it is generated in the first quadrant. It has to continue on all the 4 quadrants. Okay, that is all for today. Thank you very much.